simulation and verification processes for automated driving systems. But one of the key focus of today, I'm going to emphasize on the validation of the simulation itself. So a lot of the times we tend to focus on verification and validation processes of the automated driving systems, but we don't focus enough on the VNV of the simulation platform itself. And over the last couple of years, there's been increasing discussions around this topic. I'm going to talk a bit about some of our research and also some of the work that is happening on the regulatory forums. So before we start, I just wanted to take a very first principles approach. So I like to make things simple because it's easier to understand things when they're simple. So if you look at the VNV process for any automated driving system, be it a very simple low-speed shuttle, or it could be a very complex urban robotaxi, irrespective of the complexity of the system, the VNV process will always need only three things. It will need a set of scenarios, it will need a test environment, and ultimately it will need you to create a safety argument. Those are the only three things that you would need, irrespective of the complexity of the system. And your test environment could be a combination of PC-based simulation, a driving simulator, test tracks, or even real-world testing. It really doesn't matter. From a process perspective, you will need some sort of a test environment in which you will execute the scenarios. Now, one of the things we tend to talk about when we talk about VNV process is that generally you will always need a combination of approaches. I do not see anybody ever saying that they will only do simulation, or anybody only saying that they will only do real world testing. You will always require a continuum of test environments. So you could start at the PC based simulation, go into real world testing at the very right. So there would be this continuum that will exist. And as you move from left to right, your realism would increase, but your level of control of your system would decrease. And that's one of the reasons why a lot of people have now pushed or trying to push the VNV process towards simulation. Now that's all good, well and good, but if you try to push things out to the left, which is logical because you've got more control, then you also need to ensure that what you're getting out of your simulation is valid. Essentially, that your simulation is a valid simulation. And that's some of the bits that I'm going to talk to you about today. So before we get to that, if you look at it from an engineering perspective, if you look at the entire flow of VNV from an engineering perspective, the top level of scenarios, environment, and safety argument can be divided into certain stages of the VNV flow. And irrespective of the complexity, you will always have the same flow. So within the scenarios piece, you will start off by creating scenarios. You will then format them in a particular language so that different stakeholders can understand each other in the same manner. And then you will store those scenarios in a particular database. And once you've done that, once you have all these scenarios stored in a database, then you will make a plan that which scenarios should go in which test environment, which should go in simulation, which should go in real world testing, so on and so forth. And ultimately, you will analyze every execution to make a decision if your system is safe or not. Irrespective of the complexity of the system or the complexity of the ODD of your system, you will always have the same flow of create, format, store, plan, execute, analyze, and decide. That does not change. So if you're looking at where should you be investing your efforts in, pick a stage in this flow, and then you can start working towards that. If you feel that your expertise is around scenarios, then you might want to focus on create and format. If your expertise is around simulation, you might want to focus on execute. So in order to do this flow in a scalable manner, one of the things that we have proposed at various forums, and now it's gone into the European Regulation Act also that was adopted on 5th of August this year, this whole flow needs to be a function of the operational design domain and the behavior competencies. So what you will experience in Phoenix, what an automated driving system will experience in Phoenix, Arizona, would be very different to what it would experience in central London. but the way of going about the VNV process for both the systems would be the same of create, format, store, plan, execute, analyze, and decide. So if we can make this whole flow as a function of ODD, then we can ensure that your in-house processes do not need to worry about how different your automated driving system is. Depending upon the ODD, your process will give you the relevant artifacts. But one of the challenges that we have is, in order to operationalize this flow, we need certain set of tools and we need certain standards. And that's a lot of the focus right now for the industry. And just to talk a bit about why this ODD focus in this flow and why are we talking about an ODD-based scalable testing framework. And as I've just mentioned, if you look at it from a deployment perspective, and you're trying to deploy automated driving systems in different places, Phoenix, Arizona would give very different scenarios to Central London. However, you could have two very similar automated driving systems. So what you see in front of you is a low-speed shuttle that has been developed by a UK-based manufacturer, and they have developed a very similar system for airside of an airport. So autonomous baggage dollies or automated baggage dollies. Now, these two systems are very similar, but have two very different ODDs. So the VNV flow, while the flow remains the same, the artifacts coming out of it, like the scenarios it would experience, the kind of simulation fidelity it needs, would be very different. So that's one of the reasons why we've proposed that the whole VNV flow, be it for automated driving systems or be it for simulation, needs to be a function of the ODD. So most of the times we have a very good appreciation of ODD influencing scenario generation. I think that's very well established now in industry over the last couple of years. We have a very good appreciation that ODD influences operating conditions. Essentially, ODD means operating conditions. We have a very good appreciation that ODD influences behavior competency. Things that we do not have a very good appreciation for is that ODD also impacts scenario completeness. It also impacts safety metrics. It also, and a big focus of today's presentation, is it also impacts simulation requirements. And that's something I'm going to talk to you a bit later. So what I want to say from this side is ODD actually is impacting the entire VNV flow from create, format, store, plan, execute. So if you're making decision on tools or processes within your organization, please always consider the operational design domain and the impact it would have. So a classic example here is if your ODD includes rainfall, then you will need a simulation platform that allows you to model rainfall, model the effect of rainfall on behavior. Because without that, you will not be able to make any logical safety argument using the simulation-based testing evidence. So one of the things I'm going to talk to you about today is we'll park the plan and execute for a minute. What we'll do is we'll start off by the create stage, and then we'll go into the details of some of the stages today, just because of the interest of time. So one of the things that I wanted to highlight was the reason I'm parking simulation for now is the requirements for simulation is something that would be impacted by both the sides of the flow. So depending upon which scenarios you're going to execute, depending upon what formats those scenarios are in, that would impact the simulation requirements. Similarly, depending upon how you're going to analyze your evidence, that will also have a set of requirements on the simulation. So what we'll do first is we'll understand the right and the left side, and then we'll go delve into the details of the simulation itself. So today, what I'm going to do is talk a bit about create, talk a bit about store, and then talk a bit about the simulation itself. We won't have time to go into the details of analyze and decide. Plus, please do feel free to reach out if you have any questions around that. So let's start off with a create phase. So when you're talking about scenario creation, we've proposed at a very high level, two different methods for scenario generation, or two different philosophies for scenario generation. One is around database approach, and the other one is around knowledge-based approach. The data-based approach focuses on analyzing real-world accidents, insurance claim records, real-world data to understand what type of situations or what attributes or parameters lead to accidents or lead to near-miss scenarios. Or some of you who don't like the use of the word accidents, you can also say incidents. At the same time, we believe that we need to complement this data-based approach with a knowledge-based approach. The reason behind that is when you're just looking at a database approach, you're looking at how human drivers fail. Now that is a good philosophy to work with, but it has a very big assumption that automated driving systems will fail in a very similar manner as humans. It might be true, but it hasn't been proven as of now. So that is why we believe that we need to complement this by a knowledge-based approach where you are analyzing the system design in order to understand how the system would fail. Our philosophy for scenario-based scenario generation and scenario-based testing is that we are testing for failures. So these 8 methods that you see in front of you that we use for scenario generation are actually exposing failures in the system. And this is not just an academic exercise. So what you will see is, if any of you have been following the European implementing European Commission's implementing regulations for automated vehicles, you will see within the document Annex 3 that there is a reference to a knowledge-based approach and a database approach for scenario generation. The Act was adopted back in August, on 5th of August this year. So it's now something that is applicable for all of us. So I would highly recommend for you to have a quick read of the Act document. It's an 8 plus 80-page document, but it's a very, very good read in terms of approach towards safety assurance. So one of the things that I wanted to highlight here was the database approach generally focuses on extrinsic data, things that are impacting from outside that are leading to a failure of the automated driving system. However, the knowledge-based approach focuses on both intrinsic and extrinsic factors. So things within the automated driving system, its design that could lead to failures. And one of the methods that we use in the knowledge-based approach is a method called STPA, which stands for Systems Theoretic Process Analysis. It was invented by Professor Nancy Levison at MIT, and we've extended that as part of scenario generation process. So I'll give you a very quick run through in terms of how we use it. Now, we don't have the time to go into the details of STPA today, but what I'm going to show here is the very end of the process of scenario generation using STPA. What we end up with when we do the process, and there's a paper that we published which explains the whole process in detail, you get a set of parameters that you will be fuzzing as part of your simulation-based testing. And those parameters are actually internal parameters or internal signals within the automated driving system. So what you see in front of you is things like delay time, a sensor feed, and the delay to a particular sensor feed. And those are the kind of things that you will have to make part of your fault injection testing. So that's why we believe that the knowledge-based approach complements the data-based approach by exploring the intrinsic factors along with the extrinsic factors that could lead to failures of the automated driving system. So that was a very quick run through on the create phase. Very quickly, I'll do an overview of the store phase, and then we'll go into the simulation side of things. So once you've got these 8 methods and you have formatted them in a particular language, you will need some sort of a database to store all these. You'll get thousands, if not tens of thousands of scenarios. Now you can't just store them in an Excel file and so on and so forth. So as a result of that, we identified there was a need of the ecosystem to have a scenario database, and more importantly, to have a public scenario database. So as a result, we created the Safety Pool Scenario Database, which is the world's largest public scenario database which is available right now. And it's got over 250,000 edge case scenarios developed as a result of both knowledge-based and database scenario generation processes. One of the key things that we focused when we were creating the safety pool scenario database was the fact that we wanted to create the database that met the needs of a variety of stakeholders, varied set of stakeholders, all the way from CAF developers to tier 1 suppliers to government and regulators and to researchers. And we did a fairly extensive study around interviewing around 60 experts all over the world across these types of users. And we very quickly realized that the types of requirements that we are getting from these users are very diverse and often competing with each other. So for example, a government or a regulator might say they want the scenario to be defined in a structured natural language. At the same time, a CAF developer might say, I want it to be defined in a programmatic way so that I can execute in my simulation. Now, the two are very different. You could say they are also contradictory to each other. So we had to work around this conundrum that we had to figure out a way of how we address both our stakeholders or all our stakeholders. That led us to creating the safety pool scenario database and the corresponding scenario languages. From a use cases perspective, safety pool is catering to, as of now, ALKs, highway driving, last mile delivery, low speed shuttles, and we're just going into trucking scenarios. So I'll give you a very quick peek into the database right now, and then we can take any questions if you might have them. So one of the things that I would like to highlight is whenever you look at a particular scenario in safety pool, the first screen that you get is all the ODD tags of that scenario. Again, everything that we do is a function of ODD. So what you'll see here is all the ODD tags for this particular scenario, and then you have a definition in a language that we've created, and then you can have the exported files in terms of Open Scenario or Open Drive if you might want them. However, one of the key focus areas for us is to create an environment where the CAV ecosystem believes or buys into the concept that safety of automated driving systems should be pre-competitive. And in order to enable that, we have created a tokenized scenario exchange process, which actually means that when you get access to safety pool, you get access to a section of those 250,000 scenarios, which are in the public section. The way you get access to the rest of the scenarios is by contributing scenarios into the database. So when you contribute the scenarios, we will vet them for quality and validate them. Then we'll score them based on how similar they are to the existing scenarios or how different they are. We'll score them for criticality, we'll score them for volume, and then we'll give you tokens or credits. And then you can use those credits to unlock the other scenarios. So even if you want, you cannot buy your way into the database. And that's something that is fundamental to the philosophy of safety pool. So that's around the scenario creation and now the scenario storage. Now let's get into scenario execution and what do we mean in terms of simulation. Now, I would like to remind you of this slide where we were talking about the fact that the requirements of the simulation will come from both the scenario side as well as the safety argument side. And hopefully what you would have seen by now is, depending upon how your scenario is structured, depending upon what attributes your scenario is using, those would impart a set of requirements on your simulation environment. Similarly, depending upon how you have stored your scenarios in the database, those will impart a set of requirements on your simulation. And because your create, format, and store are all a function of ODD, implicitly, the requirements on your simulation platform becomes a function of ODD. We didn't have time today to focus on analyze and decide, but happy to speak to people if that's of interest. So what I want to show in the next couple of slides is some of the example things that we've created in terms of the simulation execution side. A lot of you would be very familiar with PC-based simulation. There are lots of software packages that are out there. So I'm not going to go into the details of all the software packages. I'm going to show you something that maybe some of you have not seen. And this is where we created a driving simulator at WMG at University of Warwick, where we wanted to test the automated driving system in a driver in the loop condition while having representative real world conditions for the system itself. And we wanted to do that for testing infrastructure, for communications, but also a big focus for us has been human factor studies. So what you see in front of you is a driving simulator which is actually inside a Faraday cage for all the comms testing, and it has got 8-meter dia, 3-meter high cylindrical screen to give an immersive view for the driver. So within the driving simulator, we can bring in any type of vehicle. You can bring in we have had a Jaguar XC. We've got a Range Rover Evoque. We've also brought in a low-speed shuttle. So depending upon what type of system that you want to test, you can drive it into the driving simulator and hook it with the virtual environment and do the testing, both on the automated control system side, but also on the human factors side. So one of the key aspects within our focus area for testing in the driving simulator has been the concept of trying to inject behind the physical sensors. So most of the times you would have seen that in testing automated control systems, you tend to inject signals behind the physical sensors. So essentially, you are creating a model of your sensor, and then based on the output of the sensor model that you send it to your control system, which is a very legitimate way of doing it. I'm not saying it's a wrong way of doing it. It's a very legitimate way of doing it, and a lot of people still do it and will continue to do it. And this is very good for testing of intrinsic and extrinsic scenario parameters. When I say intrinsic, I mean scenario parameters within the automated control system and scenario parameters that are outside the vehicle. However, what you are doing here is you're not testing the sensor hardware itself. So one of the key focus areas for us has been actually testing sensor emulation. So what we do also is, in addition to doing testing behind the sensor, we actually inject the system in front of the sensor, in front of the physical sensor. And this is all part of a real world project that we did, where we had a camera and a radar based system. So essentially it had camera and radar sensors. So we could have actually in a more traditional way of testing, modeled a camera and a radar sensor and created the corresponding sensor outputs and sent it to the control system. That's absolutely fine, and that is what we would do for a PC-based simulation. But when you go to more of a hardware in the loop kind of simulations, we would like to inject the RF signal of the radar in front of the radar sensor, not behind the radar sensor. So what we can do as part of our setup is connect the RF target emulator with the driving simulator environment and actually generate the RF signal for the radar sensor with the necessary Doppler shift as per the required velocity, angle, and the azimuth and the heading of the vehicles in the virtual setting, and send it to the radar sensor on the vehicle under test. And that way you are actually testing in front of the physical sensor. So in addition to that, we do a lot of human factors testing within the driving simulator. So what you see here is the standard Range Rover Evoque that we have in the driving simulator, which is surrounded by this cylindrical screen, which gives a very immersive experience for the driver. So in summary, what I want to say to you today is that every aspect of the testing framework for automated driving has to be and is a function of an ODD, or has a relationship with the operational design domain. And the key within that is the simulation will play a big part of this process. There's no denying the fact that there will be some level of simulation-based testing happening. However, the fidelity of the simulation that you will be using has to depend on the scenarios that you're going to execute, the format of those scenarios, and how you're going to analyze the result of that scenarios. You have to appreciate those requirements rather than just delve into, let's get the best physics-based simulation possible. That's not always the right answer. So simulation fidelity needs to be thought in a bit more methodical way as a function of ODD, as well as a function of create, format, store, and analyze and decide. More importantly, we need concrete tools, methods, and skills to convert all this philosophy into practical implementation. And we need standards. So one of the things that I forgot to mention earlier, a lot of the validation of simulation work has been discussed at the UN ECE level in VMAD SG2. So there's a document that has been published on credibility assessment for virtual testing platforms. I would highly recommend you to have a read through it. It's freely available on the UNECE wiki page. And lastly, I would like to say that me alone or no one organization or any of you alone will not be able to solve this challenge of safety assurance for automated driving vehicles. We have to collaborate with each other. We have to share data both nationally and internationally. And I'll stop here. Happy to take any questions if you might have any.